Hello everyone, welcome back to your Statistical Methods class. My name is Jessica Bray and I'll be your instructor for today's lecture. Beginning next week, we'll be covering two very important statistical techniques, correlation and regression. In order to understand those topics, we first need to discuss scatter plots, how lines and graphs are plotted using coordinate systems. Today we'll review the basics of scatter plots and how to plot points and lines on the coordinate plane. I'm assuming that about 95% of you have covered this material before, either in high school algebra or in a college math course. So my purpose for today is to refresh your memory about these topics. And we're going to be moving fairly quickly through these topics. If you haven't studied these topics before, we might be moving a little fast for you. So if you need help, your textbook links some websites where you can get additional help. Or you can pay a visit to the mathematics tutoring service at the library. And if you feel like you need extra help, please go get it right away, because you'll find that you'll be needing to understand this material right away. Alright, so let's get started by discussing the basics of scatter plots. As I said, the material we will cover is also called analytic geometry, or algebra on the coordinate plane. Here's a picture of a scatter plot. A scatter plot is a graph with two axes. The axes are both lines. The first axis is a horizontal line. That is, it runs side to side. This horizontal axis at the bottom of the graph is called the x-axis. Notice it has a number line marked along it, 0, 1, 2, 3, and so on. We call these numbers the scale for the x-axis. The other axis is a vertical line. It runs up and down. The vertical axis at the left side of the graph is called the y-axis. Notice it too has a number line marked along it. This is the scale for the y-axis. I should mention, if we're talking about one axis, we use the word axis. If we're talking about more than one, we use the word axes. The place where the x-axis and y-axis meet is called the origin. The origin is located where the scale for the x-axis is 0 and the scale for the y-axis is 0. We can draw points on the scatter plot. This red dot is a point. Sometimes I will call it a point, sometimes I'll call it a plot, but they're both the same meaning. Each point has a name. The name always consists of two numbers. In this case, the name of the point is 3, 2. Notice we write the two numbers inside parentheses, separated by a comma. These two numbers are called the coordinates of the point. They tell us exactly where the point is located on the scatter plot. The first number, the number on the left, is called the x-coordinate. The second number, the number on the right, is called the y-coordinate. The y-coordinate of the point tells us the point is located directly sideways from the number 2 on the y-axis. Now let's go through another example with this other point. The name of this point is 9, 4. The x-coordinate of this point is 9, and this x-coordinate tells us that the point is located directly above the number 9 on the x-axis. The point's y-coordinate is 4. The y-coordinate tells us that the point is located directly sideways from number 4 on the y-axis. So far, we've been drawing one point on the scatter plot at a time, but usually there are lots of points drawn on a scatter plot. When we draw points on a scatter plot, we say we are plotting the points. So in this side, 3 points have been plotted on the scatter plot. Here are the names of the points. The names always include an x-coordinate and a y-coordinate that tell us exactly where the point is located on the scatter plot. Sometimes the points on the scatter plot lie on a line. So far, we've been talking about points on scatterplots. But during the rest of today's lecture, we'll be talking mainly about lines on scatterplots. Every line we'll be talking about in this class has a y-intercept and a slope. The y-intercept of a line is the y-coordinate of the point where the line meets the y-axis. Here's the line we were looking at a minute ago. Here's the point where the line hits the y-axis, and the y-coordinate of that point is 1. So the y-intercept for this line is 1. Here's another example. Take a moment to jot down what the y-intercept of this line is. Here, the y-intercept is 6 because that's where the line hits the y-axis. As I said, every line on a scatterplot in this class has a y-intercept and a slope. I've explained the y-intercept. Now we'll talk about the slope. The slope of a line can be positive or negative. This is a line with positive slope. Its slope is 1/3, which is a positive number. There are two ways to tell if a line's slope is positive. First, if you know the slope and the slope itself is positive, then the slope of the line is positive. Now let's go through a second way to tell if the line has a positive slope. A line with a positive slope goes up from left to right. For instance, let's say an ant starts at point 3, 2 and begins walking along the line from left to right. As he travels from left to right, he goes up, and this tells us the line has a positive slope. If you start on the left and go right, a line with a positive slope goes up. This line has a negative slope, which is -1/2. -1/2 is a negative number, and that tells us the slope is negative. Also, the line goes down from left to right. A negative line always goes down from left to right. If the ant starts at point 4, 4 and walks to the right, the ant will go downhill. That means the line has a negative slope. The slope of a line is always a number, just like -1/2 or 1/3. Now let's go through how to calculate that slope. Here's the equation for calculating the slope of a line. The slope is equal to the rise divided by the run. Let's go ahead and explain what the rise and the run are. Here's one of the lines we've seen before. I've circled 2 points, 3, 2 and 6, 3. We're going to focus on the rise and the run between these 2 points. Imagine an ant starts at the point on the left, 3, 2, and then walks up the line to the right until he reaches the other point, 6, 3. As the ant walks away from one point to another, he goes up this much. This is what we call the rise. And as the ant walks from one point to the other, he goes sideways this much. This is what we call the run. Now remember, the ant travels along the blue line between the 2 points. He doesn't travel along these 2 arrows. But when he travels along the blue line, these 2 arrows show how much he goes up and how much he goes sideways. So the amount that the ant travels upward is called the rise. And the rise is the change in the vertical position of the ant as he travels from the left point to the right point. The amount the ant travels sideways is called the run. And the run is the change in the horizontal position of the ant as he travels from the left point to the right point. In this example, the rise is equal to 1 because the ant goes up 1 unit. We can see how much the ant goes up by looking at the y-coordinates of the 2 points. The y-coordinate of the left point is 2, and the y-coordinate of the right point is 3. If we subtract 2 from 3, we get 1, which is the rise. This makes sense. As the ant travels upward, his y-coordinate changes from 2 to 3, so that is a rise of 1 unit. So the rise, that is the amount the ant goes up, is equal to the y-coordinate of the right point minus the y-coordinate of the left point. In this example, the rise is equal to 3 minus 2, which is equal to 1. In this example, the run is equal to 3. That is, the ant goes sideways 3 units. We can see how much the ant goes sideways by looking at the x-coordinates of the 2 points. The x-coordinate of the left point is 3, and the x-coordinate of the right point is 6. If we subtract 3 from 6, we get 3, which is the run. This makes sense. As the ant travels right along the line, his x-coordinate changes from 3 to 6, so that's a run of 3 units. So the run, that is the amount the ant goes sideways, is equal to the x-coordinate of the right point minus the x-coordinate of the left point. In this example, the rise is equal to 6 minus 3, which is 3. So now we know the rise and the run. The rise is the amount the ant goes up, which here is equal to 1, and the run is the amount the ant goes sideways, which here is equal to 3. And our slope is equal to the rise divided by the run. The rise divided by the run is 1 divided by 3, so the slope is 1/3. This tells us that when the ant goes sideways 3 units, he also goes up 1 unit. We will always get the same slope no matter which points on the line we choose. We just calculated the slope between these 2 points. But suppose we had chosen these 2 points instead. That is, suppose the ant traveled from the point on the left, 3, 2, to the point on the far right, 4, 9. Here's the rise and the run if the ant traveled between these 2 points. The rise, that is the vertical distance traveled by the ant, is 2. The ant goes up 2 units from 2 to 4. And we can also see this by looking at the y-coordinates of the 2 points. The y-coordinate on the point on the left is 2, and the y-coordinate on the point of the right is 4. If we subtract 2 from 4, we get 2, which is equal to our rise. As we said before, the rise is equal to the y-coordinate of the right point minus the y-coordinate of the left point, or 4 minus 2 in this example. We can calculate the run in a similar way. In this example, the run is equal to 6. That is, the ant travels 6 units sideways as it walks from one point to the other. And we can also see this by looking at x-coordinates of the 2 points. The x-coordinate of the point on the left is 3, and the x-coordinate of the point on the right is 9. So to calculate our run, we get 9 minus 3, which is equal to 6. This is the horizontal change in position. As we said before, the run is equal to the x-coordinate of the right minus the x-coordinate of the left, or for this example, 9 minus 3. So now we know that the rise is 2 and the run is 6 as the ant travels between these 2 points. And we know that slope is equal to the rise divided by the run. So for this example here, the slope is equal to 2 divided by 6. And after simplifying this fraction, 2 divided by 6 is equal to 1 divided by 3, or 1/3. That's exactly the same slope we got before using those two other points. So we always get the same slope no matter which points on the line we choose. The run and the rise might be different depending on which points we choose. But when we divide the run by the rise, we always get the same slope. In our example here, the slope was 1/3. As another example, let's see what happens with a line that has a negative slope. As we said before, we can tell the slope is negative because the line goes down as the ant travels from left to right. In this case, we'll say the ant goes from the point on the left, 4, 4, to the point on the right, 8, 2. Here are the rise and the run. The rise is -2. The negative sign means the ant goes down 2 units, and the rise is -2 here. Now it may be strange that we call this the rise because the ant goes down, and usually the word rise means something's going up. But in this case, the word rise really means the change in the vertical position, and there can be negative rise when the ant goes down. We calculate the rise the same way as we always do, using the y-coordinates of the points. In this case, the y-coordinate on the left is 4, and the y-coordinate on the right is 2. The rise is equal to the y-coordinate of the right minus the y-coordinate of the left. So we'll be subtracting 4 from 2. Because 4 is larger than 2, we'll get a negative number. And that's what we want, because we know the rise here is negative. In fact, when we plug our numbers into our formula, that's what we get. 2 minus 4 is equal to -2, which is equal to our rise. Next, let's get the run. The run will always be positive if the ant is walking from left to right. In this case, the run is 4. So the ant travels sideways 4 units. We can also find the run by looking at the x-coordinates. Remember, the run is equal to the x-coordinate of the right point minus the x-coordinate of the left point. So here, 8 minus 4 is equal to 4, and that's our run. Remember, this is the run, and the run is always positive. However, as we discussed a few slides ago, the rise can be positive or negative. So we now know that our rise is -2 and the run is 4. Now we're ready to calculate our slope. Our slope is equal to the rise divided by the run. So here, the slope is -2 divided by 4. And when we simplify the fraction, -2 over 4 equals -1/2. So we've just shown how every line on a scatter plot has an intercept and slope. So we've just shown how every line has an intercept and slope. Now every line also has its own equation, and that's what we'll be talking about next. All points on a line fit this equation here. Y is equal to slope times x plus the intercept. That is, if a point is on a line, the point's y-coordinate is equal to the slope of the line times the point's x-coordinate plus the line's y-intercept. This equation, y is equal to slope times x plus the intercept, is called the general equation of a line. It's called a general equation because it's true for all lines in general. As an example, we'll use this line. It's the same one we were discussing earlier. We already figured out that the slope of this line is 1/3. And just by looking at the line, we can see that the intercept is 1. So for this specific line, the slope is 1/3 and the intercept is 1. Now we'll use the information to find the formula for this particular line. We know that all points on the line fit this equation. Y is equal to slope times x plus the intercept, because all lines fit this equation. So now what we'll do is plug in the slope and intercept of this specific line. Or in mathematical terms, we're going to substitute the slope and intercept. The slope for the specific line is 1/3, so we'll plug it in here. The intercept for the specific line is 1, so we'll plug it in here. So we substitute these values in the equation. And now we have this equation. This is not the general equation for a line. Instead, this is the specific equation for our specific line. So this is our line. And these are our 3 points we can see on the line: 3, 2, 6, 3, and 9, 4. And because these points are all on the line, all these points should fit the line's equation. And let's test this out to see if that's true. Let's begin with the point 3, 2. The point's y-coordinate is equal to 2. So we'll substitute a 2 for y in the equation. The point's x-coordinate is 3. So we'll substitute a 3 for x in this equation. So now we're left with this equation. And the question we have is, does 3, 2 fit in this equation? In other words, if we plug 3, 2 into the equation, is the equation true or correct? Remember, 3, 2 is on the line, it should fit the equation. And if we plug it into the equation should be correct. So here's our equation. Let's do some algebra to see if it's correct and true. In 1/3 times 3, we get an answer of 1. So we can substitute 1 for 1/3 times 3. We get 2 is equal to 1 plus 1. On the right side, 1 plus 1 is 2. So we substitute that in and we get 2 is equal to 2. This is correct and true. So now we know if we plug in 3, 2, the equation is true and correct. That means that the point 3, 2 fits the equation. So 3, 2 must be on the line. Let's try it out for another point. We'll use the point 6, 3 next. The point's y-coordinate is 3, so we'll plug in the value of 3 into the equation. The point's x-coordinate is 6, so we can substitute 6 into the equation. And now we have this equation. 3 is equal to 1/3 times 6 plus 1. And we have the same question as we had about the other point. Does the point 6, 3 fit this equation? Or, said differently, if we plug in 6, 3, is the equation true and correct? So let's do the algebra. 1/3 times 6 is 2. So we can plug in that 2 for 1/3 times 6. Now, when we add 2 plus 1 on the right side of the equation, we get 3. So our full equation here is 3 is equal to 3, which is both true and correct. So this answers our question. If we plug in the point 6, 3, the equation is true and correct. This means that the point 63 fits the equation. And this also means that the point 63 is on the line. So we've tested 2 points on the line, 3, 2 and 6, 3, and our results confirm that these points fit the equation. We could do the same thing with any other point on the line, but for now let's move on to other topics. During the rest of today's lecture, we'll be focusing on this topic, how to find the equation for a specific line. It's not hard to find the equation if you know 2 points on the line. As long as you know 2 points, you can calculate its equation. There are 4 steps to calculating the equation for a specific line. First, you need 2 points on the line. Second, you calculate the slope. Third, you calculate the intercept. And fourth, you plug in the slope and the intercept into the general equation of the line. Let's go through an example to illustrate these 4 steps. So step 1 is to find 2 points on a line. This is the line we've been using as an example. We actually have 3 points to choose from. We can choose any 2 of these points. I've chosen to use the points 3, 2 and 9, 4, but I could just as well use 6, 3. So we've completed step 1. We have our 2 points. Step 2 is to calculate the slope of the line. To calculate the slope, we take the rise and divide it by the run. The rise is equal to the y-coordinate of the right point minus the right coordinate of the left point. So here are 2 points that we selected from step 1. The y-coordinate of the right point is 4, and the y-coordinate of the left point is 2. So the rise is equal to 4 minus 2, which means our rise is equal to 2. Next, we need the run. The run is equal to the x-coordinate of the right point minus the x-coordinate of the left point. Again, here are the 2 points we picked in step 1. The x-coordinate of the right point is 9, and the x-coordinate of the left point is 3. So the run is equal to 9 minus 3. Or, in other words, the run here is equal to 6. So now we have the rise and the run, we're ready to calculate the slope. And again, the slope is equal to rise divided by run. So if we substitute our value for the rise, we have the slope is equal to 2 divided by the run, or slope is equal to 2 over 6. Our next step is to simplify this fraction, and when we do that, we get 1 over 3. So this completes our second step. We found our slope, 1/3. Now we're ready for step 3, which is to calculate the intercept. To calculate the intercept, we need a point from the line and the slope. Then we plug the point and the slope into the general equation of a line. Let's calculate the intercept. We need 1 point from the line. That's very easy because in step 1, we found 2 points. This is the slide we saw earlier when we did step 1, and here are the 2 points that we chose. We can choose either of these points now to use in step 3. For this example, I'm using point 3, 2. But if you want to, you can calculate the intercept using the other point, 9, 4. So now we have that 1 point from the line, which we said was 3, 2. And we need the slope, which we calculated in step 2. In step 2, we said that the slope was equal to 1 over 3. So now we have one point and the slope, and we're ready for the next part. We need to plug these numbers into the general equation for a line. Here's the general equation of a line, which we saw earlier today. Y is equal to slope times x plus the intercept. So here, we'll put the general equation. We know our x is equal to 3, and we'll plug in that number, just like this. The y of our point is equal to 2, so we can plug that for y, just like this. And we know our slope is 1/3, so we can substitute that value here, just like this. So now we do some algebra to find out what that intercept would be. The first step is to multiply 1/3 times 3. When we do that, that's equal to 1. So here we have 2 is equal to 1 plus the intercept. Next, we subtract 1 from each side of the equation. And this gives us 1 is equal to the intercept. So we have our answer for what that intercept should be. The intercept is 1. Now that we have our slope and intercept, we have enough information to write down the equation for this specific line. All we have to do is plug the slope and intercept into the general equation of a line. In step 2, we calculated the slope, which was 1/3. In step 3, we calculated the intercept, which is 1. And here's the general equation for a line. Y is equal to slope times x plus the intercept. The slope is 1/3, so we can substitute that value in there. The intercept is 1, so we can substitute 1 in for the intercept. And now we have this equation. Y is equal to 1/3 times x plus 1. Now this is no longer the general equation for a line. Instead, it's the specific equation for our line. So again, this is the formula for our specific line. It fits the form of the general equation of a line. Y is equal to slope times x plus the intercept. But now we've inserted more specific information. We know the slope is 1/3 and the intercept is 1. Here's the equation for the line and the points that fit on this equation. We obtained this equation by following the 4 steps. And this equation is exactly the same as the equation we found earlier by just looking at the graph. So it's a good sign our calculations were correct. Our 4-step process gives the same results that we would expect. As a reminder, here are the 4 steps we just used. First, we found 2 points on a line. Then we calculated the slope. Then we calculated the intercept. And finally, we plugged the slope and intercept into the general equation for a line. Now let's do another example of following these 4 steps to find the equation of a specific line. This will be an exercise posted on Blackboard, so make sure to check your Blackboard shell for the exercise itself. We're going to find the equation of this specific line. But before we find the equation, think about the answers to some of these questions. First, do you think the slope will be positive or negative? Here, the slope will be negative because it slants downward from left to right. Second question, what would you estimate the intercept to be? Here, if our calculations are correct, the intercept should be 6 because that's where the line touches the y-axis. Let's now move through our 4 steps to find the equation for this specific line. Step 1 is to find 2 points on the line. This step is pretty obvious because there are only 2 points on the line that have the coordinate points marked. Our 2 points here are 4, 4 and 8, 2. Next, we need to calculate the slope. First, we need the rise, so go ahead and fill in the blanks. The rise is equal to the y-coordinate of the right point minus the y-coordinate of the left point. Here are our left and right points, and here are their y-coordinates. The rise is equal to the y-coordinate of the right point, which is 2, minus the y-coordinate of the left point, which is 4. So the rise is equal to 2 minus 4, which is negative 2. We expected a negative number because the line is going down from left to right, so the change in position is negative. Next, let's calculate the run. Go ahead and fill these blanks in. The run is equal to the x-coordinate of the right point minus the x-coordinate of the left point. And here are our points again, 4, 4 and 8, 2. And these are their x-coordinates. So here, the run is equal to 8 minus 4, which is equal to 4. So now we have the rise is negative 2 and the run is 4. And we can calculate the slope. Again, the slope is the rise divided by the run. Here are the rise and the run. We fill them into these missing values here, and we find that the slope is equal to minus 2 divided by 4. So our slope is minus 2 divided by 4. When we simplify the fraction, we get negative 1/2. So our slope is negative 1/2. Now we're ready for step 3, calculating the intercept. To calculate the intercept, we need 1 point from the line and the slope. Go ahead and put those values here. Now for the point on the line, you have 2 choices. We know that 2 points on the line are 4, 4 and 8, 2. Some of you will probably choose 4, 4, which is fine, and the slope of negative 1/2. Some of you will choose 8, 2, which is also fine, and the slope will remain at negative 1/2. Now the next step is to plug in the point and the slope into the general equation of a line. First, write down what that general equation of a line should be. Here's the general equation for the line. Y is equal to slope times x plus the intercept. Next, go ahead and plug the point you choose and the slope into the equation. Now the calculations are going to differ somewhat depending on the point you chose a moment ago. First, let's assume that you chose the point 4, 4. The x-coordinate of the point is 4, so we'll plug that in for the value of x. So in our equation, the 4 goes where the x was. The y-coordinate of the point is also 4, so we plug that into our equation for y. So here we've plugged in that y-coordinate for y in our general line formula. And we can do the same with the slope by replacing the word slope for a value of minus 1/2. So now we have this equation, 4 is equal to minus 1/2 times 4 plus the intercept. And when we do the algebra, we have negative 1/2 times 4, which is 2. So we can place that negative 2 in for negative 1/2 times 4. Now we have to add 2 to each side. When we add 2 to each side, we get 6 is equal to the intercept. Now let's go through the same calculations using the point 8, 2. Our value for x for this point is 8, so we can substitute that in. Our value for y for this point is 2, so we can substitute 2 for y. And our slope remains negative 1/2, so let's go ahead and substitute that in here. So our full equation is now 2 is equal to 1/2 times 8 plus the intercept. Remember that 1/2 is negative. When we multiply negative 1/2 times 8, we get negative 4. And after adding 4 to both sides, we have 6 is equal to the intercept. So no matter what point you chose, you should still get an intercept of 6. So now we're ready for step 4. We're going to plug in the slope and intercept into the general equation for a line. Go ahead and take a minute to jot down what these values should be. From step 2, we know the slope is minus 1/2. From step 3, we know the intercept is 6. And we know the general equation for a line is y is equal to slope times x plus the intercept. So now, substituting our values, the equation for our specific line is y is equal to minus 1/2 x plus 6. And here's the equation we've been looking for. It's the equation for our specific line. At this point, we're done. So all in all, just remember, if you know 2 points on a line, you can calculate the equation for that specific line.